So in this lesson, we're going to look at rational functions of the form ax plus b divided by cx plus d. So to start with, it makes sense to just look at some examples of that. Okay, so we're talking about rational functions, and notice that both the numerator and the denominator are just linear functions in this case. So what do graphs like this look like? Well, to start with, I think we could probably use what we've already learned to come up with a pretty good idea about what these graphs look like. In fact, what we've learned so far in this unit and can almost describe everything that you need to know, and we'll just add a few other details. Okay, so looking at the first one, x plus 5 divided by x minus 3. I think the real thing that should jump out at you is when you look at the denominator. I mean, the first thing about looking at rational functions is to go to the denominator. X minus 3 means that there is going to be a vertical asymptote at x equals 3. The next thing we might look at is the end behavior, and in this case, we get a horizontal asymptote at y equals 1. Why is that? Well, that's because if we look at both limits, we find that we get 1 as x approaches positive or negative infinity. Why do we get 1? Well, there's a few ways of looking at it. One thing you could do is if you just subbed in large numbers for x, you would find that you get answers closer and closer to 1. But remember the idea of dividing out the biggest term as well, meaning that f of x could actually be written, if I divide by everything by x, I get 1 plus 5 over x divided by 1 subtract 3 over x. And as x gets larger and larger, these values here start to approach 0. And you end up getting something closer and closer to 1. So that means that there's a horizontal asymptote at y equals 1. Now there's no oblique or slant asymptote here. Okay, remember oblique or slant asymptotes occur when you divide something out using long division or just straight regular division. And they always happen when the graph doesn't have a horizontal asymptote, when this limit would have to be infinity or negative infinity. Okay, so slant asymptotes are when you don't have a limit equaling a constant. Okay, your limit ends up being positive or negative infinity, and then the slant or oblique asymptote is kind of like a special way to approach infinity or negative infinity. So don't get confused by that. Now we might also be interested, since it has to do with the graph, we're exploring what the graph looks like. We might want to know, like these both being 1 tells us that there's a horizontal asymptote at y equals 1, but we might be interested to know whether does it approach it from the above or from below. So let's start with looking at positive infinity. So as x gets really, really big, you're adding 5 and you're subtracting 3 on the bottom. Well, as x gets big, that becomes less and less significant. So it's kind of like you get x over x, which is 1. But notice that although x is big, the numerator is always going to be slightly bigger than the denominator, since you're adding 5 to the numerator and subtracting 3 from the denominator. Imagine subbing in 1,000. You'd have 1,005 over 997, which is really close to 1, but it's technically slightly bigger than 1. So it's going to approach it from above, or 1 plus a little bit. However, if x is a large negative number, it's a little bit different, because now if you plugged in, say, negative 1,000, you'd have negative 995 over negative 1,003. The negatives cancel out to give you positive 1, but in this case, the denominator is the bigger number, in which case it's going to be 1 from below. So that's a little bit helpful in determining what the graph looks like. We're going to find that we don't actually even need to worry about that, and most of these graphs are simple enough that you would get that correct anyways. And there's a couple other little details here. And that is, we know that there has to be an x-intercept at -5, 0, and a y-intercept at 0, -5/3. And the reason for that, an x-intercept, of course, you set this equal to 0. Here, I'll do that right now. 0 equals x plus 5 over x minus 3. And the only way to make a rational expression equal to 0 is to have the numerator equal to 0, and that happens at x equals -5. In order to get a y-intercept, you plug x equals 0. If I plug in x equals 0, I get -5/3. So pretty good idea what this graph looks like. We have two asymptotes, a vertical one and a horizontal one, and we have two intercepts. We're going to fill in the rest of the details later. We're just working on what we already know. So nothing new in this part of the lesson. We'll add that in a minute. Okay, here's the second one that was given as an example. So again, just figuring out, without learning anything new, what do we know about this? Well, clearly there's a vertical asymptote at x equals -4. The next thing to look at is the end behavior. Notice they're the same degree. The x is the dominant term. You're actually going to find there's a horizontal asymptote at y equals 2. And the reason there's a horizontal asymptote at y equals 2 is because of the end behavior. Okay, as x gets really, really large, this approaches 2. Just start subbing in large values if you want. And what you find out is that the -1 and the +4 really don't do much. It's 2 times a big number divided by the big number, which is 2. The -1 and +4 don't change things that much. Again, if you want, and I'll run through this one more time, you could divide everything by x to see that as well. If I divide by x, I get 2, subtract 1 over x, over 1 plus 4 over x. And as x gets really, really big, both of these fractions approach 0. And so the whole thing gets closer to 2 over 1, or just 2. And that gives us our horizontal asymptote at y equals 2. Just like in the last example, we could decide, is that 2 from above or 2 from below? Okay, well, if x is a really big positive number, we've got 2 times that number subtract 1 divided by that number plus 4. So I'm kind of looking and I'm saying, is this always going to be a number a little bigger than 2 or a little less than 2? Well, if you just sub in large values, you can start to see which it is. In fact, even 100 works. The top's going to be 2 times 100 minus 1, 199. And the bottom's going to be 104. So it's actually going to be a little bit less than 2 as your graph, as that's going to be, the denominator is kind of bigger than it should be and the numerator smaller than it should be. But if x is negative, that's probably going to change. So again, using just -100 as your example, that'd be -201 over -96, which is actually going to be larger than 2. The negatives divide out, but you've got a numerator that's bigger than you expect and a denominator that's less than you expect. Just use big values there if you don't quite see how that works out. So there's our horizontal asymptote, our end behavior, and then of course we could do our intercepts as well. There is an x-intercept at 1/2 because that's what makes the numerator 0. And if you sub in x equals 0, you get -1/4. So y-intercept at -1/4. As for the third example that was given, y equals x plus 2 divided by 3x minus 1. Okay, there's clearly going to be a vertical asymptote at x equals 1/3. That's what makes the denominator equal to 0. There's a horizontal asymptote at y equals +1/3. Hopefully you see that now from the other two examples. Okay, if you divide everything by x, you would end up with something that approaches 1/3. Now we could also ask and say, okay, is that from above or from below? When I look at this, I see that as x is a very large number, okay, you're adding 2 to the top and subtracting 1 from the bottom. So your numerator is slightly bigger than expected and your denominator is slightly less. So it's actually going to be slightly larger than 1/3. For example, a number like 100 would be 102 over 299, which is a bit bigger than 1/3. It's the other way around when you talk about the negative values. Okay, it'd be from below, because now it would be something like, if I use x equals -100, I have -98 divided by -301, which is going to be slightly smaller than 1/3. And then, of course, the intercepts. We have an x-intercept at -2, 0, okay? What makes the numerator 0? And then if you sub in x equals 0, you get the y-intercept at 0, -2. So there you have it. That's what we know so far, just looking at end behavior, asymptotes, and intercepts. So the next question might be, how do we figure out what the rest of the graph looks like? I mean, asymptotes and end behavior and intercepts don't necessarily describe the entire shape of a graph. So what should we do next? Well, one thing we might do is to get an idea as to what these functions look like in general, maybe we just start throwing some in Desmos. It doesn't have to be these three in particular, because we're actually going to sketch these three as if we didn't want to use Desmos. So let's just play around in Desmos a little bit right now. Okay, so I've got Desmos up here. And I can start thinking of some random equations that are in that form. So let's start with x plus 1 divided by, sorry, put brackets there, divided by 2x take away 3. And there you go. Not too exciting of a shape, but there it is. As I start changing these numbers, let's see if anything interesting happens. Change that to a 3. Okay, not much there. Change that to a 1. Okay, maybe I want to add 3 instead of subtracting 3. Okay, so that made a big difference there. Just kind of reflected it a little bit. Okay, I can make it a 3x minus 1 or a minus 5. You can see that we always get this shape right here. In fact, one thing you can do in Desmos that's kind of cool is I can actually put y equals ax plus b and divide that by cx plus d. And of course, there's no numbers there, so there's no graph, but it recommends I add a slider for a, b, c, and d. I could just click all. And then what I can do is I can go through all the possibilities and sort of slide these values around. Okay, so there I'm changing my a value. Here I can change my c value. Okay, notice that's still the same shape, by the way, if I zoom out. I can change my d value. And you can see that no matter what the a, b, and c values are, we basically end up with this same sort of shape. We just might need to zoom in or zoom out to get a better look at it. So these graphs, let's get rid of that now, all actually should look familiar because they really are the same. They belong to the same family as y equals 1 over x. And that's hopefully an equation that you're familiar with from last year. Okay, remember that you graphed functions, the reciprocal function, and did some simple transformations. And that's also on the handout. So let's go back to that now. Okay, so on this handout is the graph of y equals 1 over x. And that's what it looks like, that basic shape with a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. You can apply simple transformations and create other graphs. I've included 2 here. Okay, so notice the one on the left side of your screen looks like it has a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 4. It has the exact same shape as this graph here. You can't maybe tell from just looking, but I'm telling you that it does, which means that this equation is just y equals 1 over x minus 2 plus 4. And that's because it's been shifted to it's the same as y equals 1 over x, but it's been shifted to the right 2 and up 4. Okay, so there it is. I mean, you can tell from looking at this equation that it has a vertical asymptote at x equals 2. You can actually tell it has a horizontal asymptote at y equals 4 because 1 over x minus 2 can never be 0, but yet as x gets really, really big, this actually approaches 0. And so we have a horizontal asymptote at y equals 4. The graph looks more and more like y equals 4 as this gets bigger and bigger. You probably never thought of that way before, but now you can. And in the next one, notice there's a couple things going on. This is y equals 1 over x, but it's also been reflected, okay, in the y-axis or the x-axis. It's actually the same. So when you reflect it, that brings this chunk over here and this portion of the graph over there. So it's like there's a negative 1 over x, but it's been also shifted to the left by 1. So we replace x with x plus 1. That's all in the denominator. And it's been shifted down 2, so there's a negative 2 as well. Now, if you plug the equation I've given you in here into Desmos, you'll find your graph isn't quite look the same as this one. And the reason it doesn't quite look the same is that it's actually y equals, it's actually negative 2, not negative 1, which actually stretches it. Sorry about that, it's kind of a mess now. Which actually stretches it by a factor of 2, but you can't tell from looking that it's been stretched by a factor of 2. It just has. The only reason I've included that is to notice that, you know, y equals 1 over x, if you were to change it by multiplying it by 2 or 3 and vertically stretching, it doesn't really change the shape that much. It's still pretty similar. So y equals 1 over x and y equals 2 over x, they tend to essentially look the same. Even if you made that a y equals 3 over x or 13 over x or 20 over x, they all do kind of look the same. And so this one is, it's only important to notice that it's not 1 over x, it's negative if it's been reflected like that. So that's that equation. Okay, so I bring that up because the graphs that we looked at, like this one right here, tend to have that same shape. And we can actually take this equation and rewrite it so it looks like these equations right here. And let's look at how we do that now. So we're going to take the equation f of x equals ax plus b divided by cx plus b. That's an equation like this one right here. And we're going to rewrite them. And the form we're going to rewrite them in is going to look like this. Okay, that's y equals a over b times x minus h plus k. And those letters aren't super important, but we're just making this equation here look like the equations that we're more familiar with, like this. So how do we do that? Well, we actually can use long division to do that. Now, it's very strange to divide two linear equations using long division, but you can do it. Let me show you what you get. Okay, so I'm taking x plus 5 and dividing it by x minus 3 using long division. So I set it up like this. Okay, remember that, make sure you get them in the right spot because it can be hard to tell. How many times does x minus 3 go into x plus 5? Well, it really only goes in one time. 1 times x gives you x, and 1 times negative 3 gives you negative 3. And then we subtract, and the x's cancel out. I mean, I want to put whatever number here makes the x's cancel out or subtract out. And then 1 times negative 3 is negative 3. 5 subtract negative 3 is 8. Okay, now I'm going to rewrite this with the remainder written as a fraction. So basically, I'm saying that x plus 5 divided by x minus 3 is equal to 1 with a remainder of 8. So 1 plus 8 over x minus 3. Of course, it doesn't matter which way we write this equation. So that basically says that, look, f of x can really be written as 8 over x minus 3 plus 1. Done. It's a very easy division or a quick division. So we've basically taken something, and it's sort of like it's very similar to when we used polynomial long division in the previous lessons. We're taking something that's simplified and kind of breaking it up into parts. Because I can look at this and I can relate this to the graphs on the previous page. Okay, this is going to have a vertical asymptote at x equals 3, horizontal asymptote at y equals 1. Now keep in mind, we already knew that. We knew that from looking at the end behavior and the denominator. But it gives me the shape as well. Remember that the 8 doesn't really do much to this shape. That's just a vertical stretch. And so I'm ready to convince, I'm now convinced what this graph looks like. Let's just sketch it. Okay, so I've started with my asymptotes at x equals 3 and y equals 1. Always a good idea to sketch those first. Now keep in mind, we did already determine quite a bit about this equation f of x. We found the x and y intercepts for one thing. If I just back up. Okay, they were at -5 and -5/3. Okay, and also, of course, we found those asymptotes already that I drew. So -5, so let's start with the x and y intercepts to make sure we get those in the right spot. Okay, so x equals -5. There's going to be an x-intercept somewhere down here. Oh, sorry, that's not correct. Somewhere down here. And -5/3 somewhere in here. And we know now that this graph looks a lot like these graphs here. It looks a lot like 1 over x with a vertical stretch factor 8, which actually doesn't change the graph very much. And then it gets shifted, in this case, shifted to the right 3 and up 1. There's no reflection, so I'm going to have one part of the graph is right here. And the other part's going to include our x and y intercepts. Is something like that right there. It's not super easy to draw a graph on this tablet I'm working on, but there you go. Let me see if I can just fix that up just a little bit, make it a little bit better. And there you go. Let's do the same thing for the next example. So next on g of x, we analyze this already a little bit. We found the x-intercept of a half and the y-intercept of negative a quarter. Obviously, there's a vertical asymptote at x equals -4. We also found the horizontal asymptote of y equals 2, though after we do long division, that horizontal asymptote of y equals 2 is going to be really obvious, even if we didn't do that part before. So again, we're going to divide. So we're going to divide 2x minus 1 by x plus 4. So we need a 2 here. 2 times x gives me 2x plus 8. And then I subtract. -1 minus 8 is -9. And so I can rewrite g of x as being 2 plus -9 over x plus 4, which looks a lot nicer if it's written as g of x equals -9 over x plus 4 plus 2. And now we have this written in a nice form. We can see that it's the graph of 1 over x shifted to the left 4 and up 2. So there's a horizontal asymptote at y equals 2. It's also been reflected and stretched. The stretch isn't a big deal, but the reflection does change what it looks like. So we're ready to sketch this now. So there it is with my horizontal asymptote at y equals 2, my vertical asymptote at x equals -4. We also had intercepts at a half, 0, and -1/4. So very close to the origin there. There's a point right there and a point right there. Okay, remember that y equals 1 over x looks like this. But once you make it negative, that reflects it. So we're not here and here. Instead, we're here and here. So we need to graph that, and we're going to get something like this right here. I'll try my best to do this. And like that right there. There's the general shape of that graph with the intercepts, which you can obviously label, okay, and my asymptotes. Of course, you can put this in Desmos to get a better picture of it as well, but the whole idea is we're trying to use algebra to show why the graph looks the way it does. Now, I will point out that converting it from, like, we have basically two different forms. We've got the equation written in this form right here, and we've got the equation, of course, written in this form right here, and they're equivalent. The way that I've shown you how to take this and break it up into this is using division. I think it's the simplest way to just do this quick little division. If you're not sure that if you're not convinced that that works, what you could do is notice that if you make a common denominator here, you multiply 2 by x plus 4 over x plus 4, simplify it out, and you will get back to here. There are other methods for taking this and converting it to this right here. Okay, I've just focused on this one. If you watch the video from CEMC that I've given you the link to, you'll find that they show you both ways of going from here to here. They show you division, and they show you another trick as well that you can use. Okay, one more example that we'll do. Okay, so for our last example, we're looking at y equals x plus 2 divided by 3x minus 1. So we'll start with that division again. How many times does 3x minus 1 go into x plus 2? Now my guess is you can probably tell right away this one's going to work out a little bit different. First of all, when doing the division, 3x minus 1 will go into x plus 2. It will go in there only a third of a time. So we have 1/3 here. A third times 3x gives us x, and then we get minus 1/3. Subtracting gives 2 subtract -1/3 is 2 plus 1/3, or 2 1/3, which is 7/3. So what's that mean? Well, it means that we can start by rewriting this by saying, now that we've divided it, it can be rewritten as 1/3 plus 7/3 over 3x minus 1. Rewriting that gives us y equals, so 7/3 divided by 3x minus 1 is actually the same as 7 over 3 times 3x minus 1 plus 1/3. So there it is, and it's not as nice looking as the other ones, but do keep in mind we've already found out a lot of things about this equation. We know that there's a horizontal asymptote at 1/3, and we can see that. Now the vertical asymptote is technically at x equals positive 1/3, so this has actually been shifted to the right by x equals a positive 1/3. There's been a stretch of vertical stretch of 7. So compared to 1 over x, basically has the same shape. There was no reflection done, so it's going to end up looking like that with our asymptotes in the correct spot. So we might want to do is to go back and look at the information we already figured out for this equation, which of course is right here. We know that it has the vertical asymptote at 1/3, horizontal asymptote at 1/3, and x and y intercepts both at -2. So I'm going to sketch this now, starting with our asymptote. So there you see my asymptotes. Okay, I remember that I know the intercepts, which help me as well. They're both at -2, so I can put one in here and one down here, let's say, compared to 1/3. And then I've got a branch up here. Oh, it's so hard to draw on here, sorry. And one looks like that right there. And that's your curve. Looks like all the rest. I mean, they all kind of look the same. They have asymptotes in different places. And you kind of almost, as you work on this, realize that the big thing is knowing whether this number up here is positive or negative. If we look back at the other one too, you can see that. So here it's negative, so you end up getting this. Here it was positive, so you end up getting them like that. Okay, that's it for today's lesson. There's some questions for you to try, and like I said, if you want, there is another video you can watch from University of Waterloo that shows you this method as well as some other methods as well. I feel like when you're sketching these, there's so many ways to determine what's going on that they're not usually too bad. Okay, thanks.